In our last lecture, we had an introduction on the image segmentation, where we had said that the primary objective of image segmentation is to partition the given image into a number of different objects, so that we can attempt the results of the segmented images to have object identification and other tasks. And we said that this has got extremely wide applications, ranging from target detection, automated visual inspection, analysis of remote sensing images, and many other applications. And we had also said that there are two primary approaches on the image segmentation. The first is segmentation based on discontinuity detection, which we had started in the last class, and the second approach is based on the similarity of various pixels. And we also said that in case of dynamic or time varying images, one can have the motion cues, okay, in order to achieve image segmentation. Now we had started with the image segmentation based on discontinuity of intensity values in the pixels, where we had said that there are two approaches which are normally followed. One is the local approach, which we had decided in the last class, where basically after applying any edge detector operator, we were taking the edge pixels and then we were grouping the edge pixels according to some similarities. And there we said that basically we were applying a local neighborhood, that is to say a 3 by 3 or a 5 by 5 local neighborhood around the pixel of interest xy, and we were finding that in that local neighborhood, whichever other edge pixels were there, we were finding the similarity of the edge strength and the similarity of the edge angle, and grouping the pixels accordingly. And we were keeping a track by maintaining a record or list of all the pixels which can be clubbed into any particular group. Alright, and thereby our primary objective was to detect the object boundaries. Now this was, as we said, that this was primarily local, because we were using only a 3 by 3 or a 5 by 5 local neighborhood region to search for the other edge pixels. And then we had said that one type of global approach could be whereby we have n number of given edge points, and then we were trying to fit straight lines between every pair of points, and then searching that which is going to be the best fit straight line. And there we said that we are going to have a search complexity of the order of n cube if we have to detect the straight lines out of n number of points. So obviously this was computationally prohibitive, and the approach which we are going to discuss now is the Hough transformation based approach. Alright, now before we begin Hough transformation, okay, let us look at some very elementary concepts of it. Let us say that we have the xy plane like this. Supposing this is the x direction and this is the y direction. So this is an xy plane that we have defined, and on the xy plane I take any particular point, okay, and let us say that the coordinate of this particular point is xy, and let us also say that its intensity is f of xy. Now tell me that if a point xy is given to us, alright, then and supposing that xy is an edge pixel, and we are interested in finding out that the linear edge segments which are passing through this point xy. Now how many straight lines can pass through this point xy? Only 4? Assume a continuous space, okay, assume a continuous space, and there could be infinite number of straight lines which one can draw. If this is the xy point, okay, I can draw a straight line like this, I can draw a straight line like this, So infinite number of straight lines are possible from this point. Now, what is the equation of the straight line? Since, let us say that the point is not x, y, the point is a particular point, let us say xi, yi. Let us take a particular point whose coordinates are xi, yi, and the straight line which passes through the point xy, yi, that can be described by an equation like this. B is equal to a xi, okay, or rather we can say y is equal to a xi plus b. Yi is equal to a xi plus b. This is the equation of a straight line where a is what? A is the slope and b is the intercept. Now, how do we obtain all these different straight lines, all this infinite number of straight lines? By varying a and b. If we vary a and b, then we can draw infinite number of straight lines passing through this point xi, yi. Now what I am going to do, I am going to write this same equation in a bit of different form, okay, and I will tell you how I write it. Now the same straight line equation yi is equal to a xi plus b, let me write it as b equal to minus xi a plus yi. No big thing is there, okay, it's only some algebraic manipulation that I had written it as b is equal to minus xi a plus yi. Now this time, now what I want to do, I want to vary a and b and draw a number of straight lines. Now supposing I try to represent the straight line not in the xy plane but in the AB plane. Since we would like to keep both a and b as variable, let us take this as the a axis and this as the b axis. And we would like to pass a number of straight lines passing through xi, yi. Okay, xi, yi is a point which is given here, and we would like to pass a number of straight lines by varying a and b. Now tell me that how many straight lines do I get in the AB plane? I am varying a and b, alright, and I will be getting only one straight line corresponding to one xi, yi. I have got only one point xi, yi. I have started with only one point and I will be getting a straight line, okay, just one straight line I will be getting corresponding to the point xi, yi. Alright, so what was a point in the xy plane has now become a straight line in the AB plane. I am no longer, mind you, I am no longer in the xy plane, I am right now in the AB plane. I have made a and b as variable, so a and b are changing, okay, and accordingly my straight line is also changing. Alright, now let us say that I have got a second point whose coordinates are xj, yj, and mind you, this particular straight line is unique, one and only one for the point xi, yi. Now let us say that I have got a second point whose coordinates are xj, yj. Now corresponding to this particular straight line, corresponding to this point xj, yj, in the AB plane, what should I get? I should get yet another straight line. Alright, so let us say that this is the straight line which we get for the point xj, yj. So the two straight lines are, in general, the two straight lines are meeting at a particular point. Okay, and let us call that particular point as AIBI. Supposing AIBI is the point of intersection of the two straight lines. In the AB plane is the point of intersection of the two straight lines in the AB plane. Now, what does that indicate?
The slope and the intersection of these straight line xi, 20 xi, y and xy.
Okay, I mean somebody has given the correct answer. Actually, we have got 2 points. One point is xi, yi, and we have passed a straight line through that. We have got yet another point xj, yj, and we have passed yet another straight line through that. And the two straight lines have intersected at some particular value of AIBI. At that particular value of AIBI, we are having, that particular value of AIBI dictates the slope and the intercept of the straight line which passes through xi, yi and xj, yj in the xy plane. So now the picture is something like this. If I draw the xy plane, okay, I have got 2 points. One is xi, yi, and the other point is xj, yj, and the two straight lines, there is a straight line passing through these 2 points xi, yi and xj, yj, and in the AB plane we are having one straight line like this, another straight line like this, and they intersect at a point which is known as the AIBI. So obviously AIBI is a point in the AB plane, and a point in the AB plane becomes what in the XY plane? It becomes a straight line in the XY plane. This is a point AIBI, it becomes a straight line in the XY plane, and a point in the XY plane becomes a straight line in the AB plane. Alright. So now what we will do, that instead of trying to process the image in the XY plane, we will try to process the image in the AB plane. Okay, and we will see that why should we do that and what is the advantage that we are trying to get in that process. Why don't we remain in XY plane in order to detect the straight line? We are not doing that, we are going over to the AB plane. And let us first tell you that what is the principle behind it, okay, or how exactly we do that. Okay, that's what we are going to discuss. Now please note here that every straight line in the XY plane will get mapped to a point in the AB plane. Alright. Now that means to say that if there are, if we have a number of points, let's say we have got a number of collinear points on this straight line, a large number of collinear points. Now this will give rise to what in the AB plane?
One point with lot of lines passing through.
Correct. This will give rise to one point with lots of lines passing through it. Now if it is possible for me to keep a count of how many lines are passing through this particular point in the AB plane, okay, then that dictates what? Supposing I find that n number of straight lines have passed through a particular point AIBI in the AB plane. What does that mean in the xy plane? It means that there are n number of collinear points in the xy plane. Alright. So what happens that every point will get mapped into a straight line in the AB plane, and let us say that how we are going to tackle this problem in the discrete space, because after all we are not going to operate in the continuous domain, we are going to operate in the discrete domain where all the values of A and B will not be allowed, but only a discrete set of values of A and B will be allowed. So what we will do, supposing we draw the AB plane, okay, in an enlarged form like this, okay, and let us say that we have these many partitions for A, okay, and let us say we have similarly a large number of partitions for B, okay, and we will be allowing only the discrete values of A and B. That means to say A can be either 1 unit, 2 unit, 3 unit, 4 unit like this, and if this is the axis, if this is the origin 0 0, then even B also can have all the discrete set of values which are shown over here. Now what we will do, when we detect a particular, when we have any particular point in the xy plane, I have already said that that will get mapped into a point in the xy plane will get mapped into a straight line in the AB plane. So what we will do, we will apply the equation B equal to minus xi A plus yi, okay, and then what we are going to do, we are given with a particular xi yi, that xy yi is given to us, and now we will keep on varying A. We will first take A equal to 0 and see what value we get for B, okay. Supposing we have taken, supposing this bin is for A is equal to 0, for A equal to 0 this is the column, A equal to 1 this is the column, A is equal to 2 this is the column, like this, and this is for B equal to 1, B equal to 2, B equal to 3, like this, okay. Now when I find that corresponding to A is equal to 1, the value of B is, let's say over, let's say the value of B is something like this, somewhere over here, we will be incrementing that particular cell. Supposing we have we have divided this entire AB space into a large number of cells. Supposing we have K number of partitions for A and L number of partitions for B. So we have divided the entire AB space into K into L number of cells. So we have chosen value of A equal to 1 and find out that what is the corresponding value of B, that we calculate from this equation, and corresponding to that value of B we will be incrementing that cell. Initially we will clear all these cells. We start with all the cells initialized to 0. We are going to keep a count on how many times the accumulated cells, okay, will be incremented. Is this problem clear to you? We have got a large number of accumulated cells, okay. For A we have made K number of partitions, for B we have made L number of partitions. So really speaking, there are K into L number of accumulated cells, and initially we are clearing all the accumulated cells. So every cell value is kept to 0 initially. Now we are taking the point xy yi, okay. The first point is xy, the first point is xi yi, and we now begin with A equal to 1, the first column, okay. We take the first column, substitute A equal to 1 and get a value of B. So that particular AB cell is incremented. Okay. Then again go over to the next value of A. Okay. If you had started with A equal to 1, okay, the next value of A will be A equal to 2. Corresponding to A equal to 2, find out what B it is. Supposing we have got B equal to 1 over here. Supposing now we go over to A equal to 3 and find that the corresponding value of B is here. So we increment that cell. All other cells are having a value equal to 0. Come to next, the value is 1. Come to next, the value is 1. Like this, supposing we keep on filling up. Okay, and we have got, the accumulator condition now like this. Alright. Then we find a second point. Okay, let us say the second point is xj, yj. Corresponding to the second point, there will be yet another straight line. Alright. And supposing that straight line, and for that straight line, supposing when I substitute b is equal to minus xja plus yj. Okay. Then corresponding to this xj, yj, I will again start with a equal to 1. Alright. And I will get a different value of b, isn't it? Supposing the value of b is over here. Come to b equal to, come to a equal to 2. We get the corresponding value of b somewhere here. Come to a is equal to 3. Supposing this is the point which we get. Now already this point is having a count equal to 1. So now the count will become 2. And the other cells will get incremented corresponding to xj, yj. Alright. Now we take the third point, which is say xm, ym. Corresponding to xm, ym, there will be yet another straight line that will pass through. Supposing 1, 1, 1. This cell will get incremented and become 3, 1, 1, 1. Now, if we examine this cell array after, after substituting the equation for 3 xy points, okay, I took xi, yi, I took xj, yj, I took xm, ym. After taking these 3 points, okay, the situation of the accumulator is somewhat like this. What is the significance? After examining this AB cells, okay, after examining the cells in the AB plane, what I find is that at this particular point, okay, we are having a peak equal to 3, okay, and this indicates that through this point, okay, in the AB plane, I have passed, this count has 3, this count of 3 has come because I have got three points, okay, which, through which I can pass a straight line. If these 3 points happen to be collinear points, okay, then I will be having count of 3 here. So this corresponds to this particular value of AB indicates that there are 3 points, or there are 3 straight lines passing through this particular point. Alright. So what we will do, we will keep on picking up the cells which are having high counts. Alright. Is this approach clear to you? Okay. So I again repeat what I did. I took xi, yi and found out that which beans are getting accumulated, which cells are getting accumulated. I took yet another point xj, yj, saw how many cells are accumulating. Again I took a third point xm, ym, saw how many cells got accumulated. Like this I can go on, okay, for a large number of edge points. Typically we will be having n number of edge points, okay, and we will be incrementing the cells corresponding to this particular equation. Okay, given by this equation, we will be incrementing the cells, and we will be picking up those cells which are having large number of counts. If I get a count of 3, what does that really indicate? Count of 3 indicates that 3 points have contributed to a straight line. Okay, count of 1 indicates that only 1 point has contributed to a straight line. So this is not a real straight line, but since 3 points have contributed to a straight line, we can say that this is a genuine straight line, since 3 edge points have contributed to this. Okay, and if I have n number of edge points, okay, which are collinear, if we have n number of collinear edge points, then we will be having a count equal to n for this particular beam. Is this understood very clearly? Now the pertinent question is that how many divisions do we make for A and B? How many cell divisions do we make? What is the range of A and B? Definitely we have to draw the accumulator cells for A that for values of A within the limits A mean and A max, where A mean is the minimum value of slope and A max is the maximum value of slope. And similarly, the range of B is B mean for minimum value of intercept and B max for maximum value of intercept. Okay, so within the range A mean to A max, I will be dividing A into k number of cells, and within the limits B mean to B max, I will be dividing the B axis into L number of cells, so that I have totally k into L number of cells. Now tell me, what is A mean and B mean? A mean is 0. Okay, I mean considering the magnitude part of the slope. Okay, A mean, the magnitude value of A mean could be 0. Okay, what is going to be B mean? 0 again. Okay, if we consider the magnitude part. Okay, what is going to be A max? Infinite. B max? Again infinity. And if you don't take the magnitude part, you take both magnitude and sign, then the range of A mean to A max is minus infinity to plus infinity. The range of B mean to B max is minus infinity to plus infinity. So do we think that whatever we have discussed is feasible? Whatever we have discussed is absolutely not feasible, because in computations I cannot have limits ranging from minus infinity to plus infinity, or for slope as well as for intercept. But really speaking, such situations will arise. What happens when we have a vertical line? And vertical line we are going to have. Vertical lines will be there in images, so this is unavoidable. So there is no point in doing any kind of approximation or things like that. Okay, we really cannot implement this thing in practice. Our XY domain was much friendlier. The XY domain was much better as compared to this new AB space which we have created. Okay. Okay, let us try to think of some advantages of this AB plane. After all, when we are trying to detect straight lines globally in the spatial domain, we had indicated, okay, in the earlier class, we had discussed that we are going to have order of n cube number of computations to detect a straight line. Okay, whereas in this case, okay, how many number of searches are involved totally? Pardon?
n square.
All right. I mean, the total space is n square. Okay, no doubt. But in order to search for a particular straight line, okay, what we are going to do? We are, we are going to examine the cells for every A. Okay, this A, this A, this A, and how many such A's are there? There are k number of cells, and for n number of points, we are going to search it for k into n. Okay, so the order of search is kn. Okay, so we have reduced the search space for detecting straight lines. So this is computationally possibly easier, but implementation wise we have a difficulty. So one can always argue that parameter space has got some benefits, no doubt, because if instead of going from the original xy space to this AB is known as the parameter space. This AB plane, we are describing it as the parameter space. So in the parameter space, the number of, the searching for straight line is obviously simpler. Okay, we have order of n number of searches, but we find that there is a difficulty that in the range minus infinity to plus infinity, we have to accommodate the cells. This is for A, and for B again, the range is minus infinity to plus infinity. So what we do? Do we throw away the parameter space concept? Let us keep the parameter space concept, okay, and say that in what alternative manner we can write a straight line. Okay, we have the straight line. Supposing we have a straight line in the xy plane, and the straight line is like this. Now what we can do, from the origin we can draw a perpendicular on this xy, and supposing the length of this perpendicular is rho, okay, the length of this perpendicular is rho, and the angle which we trace from this axis, we are calling that angle as theta. Okay, so this is our perpendicular, and rho is the perpendicular length, and theta is the angle. Okay, so what is going to be the equation of this straight line in terms of rho and theta? In terms of rho and theta, if we specify rho and theta, the straight line is uniquely specified, isn't it? The straight line is uniquely specified in the xy plane. So what is going to be the straight line's equation? Rho is equal to x cos theta plus y sin theta. In earlier case, we were taking the equation as y is equal to ax plus b, and in this case rho is equal to x cos theta plus y sin theta. Now, yes please, what's the question?
In this axis, perhaps x and y will be interchanged.
X and y will be interchanged. 1 minute. And the yes, you're right, absolutely. Yeah, we will be defining the, let us define the x-axis this way.
And we can also
Correct. Let us have this as the x-axis and this is the y-axis, and now the equation is rho is equal to x cos theta plus y sin theta. Okay, thank you for this correction. Now, in this, if I take any point in the xy plane, okay, what does that correspond to the rho theta plane? So now our parameters are rho and theta, not a and b. the parameters are going to be rho and theta. So from the xy space, we will be going over to the rho theta space. So if I have a point in the xy plane, okay, what does that mean in the rho theta plane? Is it a line, a straight line, circle? Anybody else? Is it a line or a curve? Tell me. That's a curve. Curve of what nature? Curve of sinusoidal nature, isn't it? Okay. It gives rise to sinusoidal curves basically, because the equation is x cos theta plus y sin theta. So it gives rise to sinusoidal curves. Alright. So any point in the xy plane will be mapped into a sinusoidal curve in the rho theta plane. And if I have a number of collinear points in the xy plane, what does that mean in the rho theta plane? I repeat the question. I have got a number of collinear points in the xy plane. What shall I get in the parameter rho theta space? I will get same curves, okay, but the curves will pass through what? Again, these curves are going to intersect at a particular point. If I have n number of collinear points in the xy plane, alright, they are going to intersect, okay, at the same point, okay, n number of times. There will be, we will be having, if I take n number of points from the xy plane in the rho theta space, supposing this is our rho and this is our theta, alright, and we are going to have, for one point we are going to have a curve like this, for another point we are going to have a curve like this, for another point we are going to have a curve like this, okay, and if there are n number of points, then the point of intersection will indicate what? The point of intersection will be a particular rho I, theta I, through which how many curves should pass? N number of curves should pass through rho I, theta I in the parameter space. Alright? Okay.
We have just converted from one line to rho theta space. We have not converted any point from xy space to rho theta. You are drawing a perpendicular on a line.
1 minute. Let me clear the concept further. We have taken a straight line in the xy plane, okay, and the straight line's equation is described as rho is equal to x cos theta plus y sin theta, where rho is the perpendicular distance from the origin and theta is the angle with respect to the x-axis. Okay. Now, my parameters are rho and theta, and we are now going over to the rho theta space instead of being in the xy space. Alright. Now, I take a particular point, let us say I take x1, y1. Okay. I take a point x1, y1, and corresponding to that point, okay, what I will do? I will decide on a particular value of theta, okay, and compute rho according to this x cos theta, x1 cos theta plus y1 sin theta, okay, and then I will be varying theta. For a particular value of theta I get a particular value of rho. Again, for the next value of theta I get next value of rho. Like this I will be tracing a curve. Alright. So I trace a curve. So what was a point in the xy plane becomes a sinusoidal curve in the rho theta space. It becomes a sinusoidal curve in the rho theta space. I take the second point x2, y2. And by taking that second point, I will be tracing what? I'll be tracing yet another curve. Okay, and what does the point of intersection of these two curves mean? Tell me the physical concept of that. So that means to say that that particular rho I, theta I, which is the intersection, okay, corresponds to the value of rho theta which I get by the by joining the points x1 y1 and x2 y2. Okay, if I join, I take the xy plane, okay, and I join x1 y1 and x2 y2. Okay, it is going to have some value of rho theta, and what is that rho theta value? It is rho I theta I. Alright, so the point of intersection gives me that value of rho theta which passes through, and the value of rho theta corresponding to the straight line joining x1 y1 and x2 y2. Now instead of 2 points, if I have n number of collinear points, I have got n number of collinear points whose coordinates are x1 y1, x2 y2, etc. up to xn yn. Then for each of these points I will be having one sinusoidal curve. Okay, and since they are collinear points, there is a real straight line that passes through these points, this n number of points in the xy plane. So it is going to have one particular unique value of rho and theta, that straight line in the xy plane. So all these n collinear points, okay, will give rise to n number of curves in the rho theta space, and those curves will intersect at the particular value of rho theta, which is the rho theta for the straight line passing through this n number of points. Is this clear to you now? Right? So again the concept is very similar. We are going to examine the rho theta cells. So we are going to divide the rho theta plane into a number of cells. Okay, supposing this is the direction of rho, okay, and this is the direction of theta, then we have a large number of rho theta cells like this, okay, and we are going to examine what? Those cells which are going to have high values of count, okay, and high values of count indicate what? It indicates that those many number of collinear points, okay, are there, okay, and we can group them into straight line. Alright, so if I have a value of if I get some high value of count on this accumulator cell and on this accumulator cell and possibly on some other accumulator cell over here, okay, and very low value of counts on the other cells, what does it indicate? There are 3 different straight lines which are there, okay. Now tell me one thing, that if in the xy plane, supposing this is x and this is y, in the xy plane, if I have 2 straight lines like this, okay, and I have chosen the straight line so that both these straight lines, line number 1 and line number 2, are having the same value of rho and theta, okay. So what should I get in the parameter space? If I have in one number of collinear points corresponding to segment line segment number 1, and if I have in 2 number of points corresponding to line segment number 2, okay, what is the count that I am going to get in the cell corresponding to that particular rho I theta I? N1 plus N2. But from that, what should I infer? Should I infer that there are two straight lines? Physically there are two straight lines. But I will infer that there is only one straight line contributed by N1 plus N2 number of pixels. So what should I do? Just keeping a record of the accumulator count is not enough. We have to also see that, we have to keep a record of which pixels are contributing to that cell count, okay, and we will also maintain a list of all the pixels which are contributing to the incrementing of that particular accumulator cell. So if I can record all the N1 pixels coming from line segment number 1 and all the N2 pixels which are coming from line segment number 2, in this case what I will do later on is I will examine the coordinates of all these pixels and find that since the coordinates of these line segments and the coordinates of pixels belonging to these line segments are widely different, okay, physically they mean two different straight lines, okay. It can easily happen. Let me tell you, supposing I have some industrial object, okay, which is having a shape like this. Supposing I have got an industrial object of this shape, okay. This is a straight line, this is a straight line, and these two are having identical rho and theta values, okay. But if I examine this set of pixels, coordinates of these pixels and coordinates of these pixels, okay, I can clearly see that these belong to one straight line and this belong to a second straight line. Now supposing, in the last class I was mentioning about a problem that when you are trying to detect the edge for an image which is having a very poor contrast, okay, you will observe what? You will observe breaks in the line segments, okay. So supposing for an object of this nature, okay, you are getting the edge pixels of this form. There are some gaps like this, okay. So in this case, what can you do? You can simply bridge the gaps, okay. So that means to say that by examining the contributing xy pixels to a given accumulator cell in the rho theta space, okay, we can see that if the xy values are widely different, okay, then they correspond to two different line segments. Otherwise, if they are close enough to each other, then all of them can be grouped into a single straight line segment. Like here, I could be having some small gaps. I could be having 1, 2, 3, 4, 5 such gaps, okay. But all these gaps are very small, so that if I take the coordinates of all these contributing pixels, okay, I can ultimately detect that this is one and the same as saying that we have a straight line running from this endpoint to this endpoint, alright. So thereby, in the detected line segment, we will not be having any breaks, because I discussed in the last class that having such discontinuities in the line segment, okay, becomes a very severe problem in detecting the object boundaries. Is that understood? Now let me summarize the various steps, okay, which we are doing, okay. At first, so edge linking based on Hough transform. At first, we compute the gradient of an image, compute the gradient of an image, or rather, you detect the edge segments, okay, detect the edge pixels. This is for the detection of edge pixels. Alright. And after detecting the edge pixels, you specify the subdivisions in the xy plane, the subdivisions in the rho theta plane, and then in the third step, you examine the counts of rho theta accumulator for high pixel concentrations, and in the fourth step you examine the continuity between pixels in a chosen cell. Okay, so if we carry out all these 4 steps, okay, we can detect the individual line segments which are present in an image, starting with a given set of edge pixels. Alright, so all these incrementing accumulator array and all these things we have to do for by considering every such edge pixels. Is that clear to you? So wherever we have such noisy pixels, wherever the edge pixel does not correspond to any object, okay, it just corresponds to a noise. In that case, for those edge pixels we will be having lower value of accumulator counts, okay, whereas for collinear points, okay, they will give rise to high accumulator values, okay, for the corresponding value of rho theta. Alright, so we will be discussing about other approaches to image segmentation in the next class. Thank you.